Hey ladies, it's time for a digital lesson. Okay, so I was looking for some practice on differential equations. I found some good ones. I thought I'd work through most of one with you, and then I'm going to give you a couple for practice. I don't think if I go through these that there'll be any big surprises, so it'll be good practice. All right, so remember on the free responses, there's like one little, I don't know what they call this again, but this applies to every piece of it. Now, we have, just for space-wise, we have that, sorry, on the top, and then we have 1, 2, 3 pages that have whatever on it, but we have to keep in mind that this applies to all pieces. So don't forget that, because that sometimes is a big thing. Okay, first thing, on the axis provided, part A, first of all, we have a diffie Q. Now, take a look at this diffie Q. It's not going to be one that we can separate like we did on the last lesson, because there's no way you could separate that. So they would never give you one that they would say, solve it, by separating. So anyway, keep that in mind. On the axis provided, sketch a slope field for the given differential equation at the 9 points indicated. Okay, so this thing is sitting here, the slope field, the dots. All right, I did this chart just so that I didn't want to take the video to do that, but you don't want to take a whole lot of time creating this chart, because that's time that you're not doing something. So if you can do this without the chart, fine. If you can't, then develop some system. I did, okay, I'm going to go through the zeros, x equals 0, x equals 1, x equals -1, and then I've gotten everything covered. Okay, and remember, you're going to plug in x equals 0 minus 0 plus 1, so the dy dx is 1. Okay, x equals 0 minus 2 times 1 minus 2 plus 1 equals -1. And you go through these. X equals 0 plus 2 plus 1 equals 3. X equals, let's see, 1 minus 0 plus 1 equals 2. X equals 1 minus 2 plus 1 equals 0. X equals 1 plus 2 plus 1 equals 4, so on and so forth. 0, -2, and 2. Okay, just arithmetic, just be careful. Okay, so now remember, here's what they're going to be looking at. They're going to be looking at they're going to be checking, they're not going to look at your charts. Okay, you're just going to say, all right, now, and they're just going to look at relative steepness at each point. So the 0, 0, we'll start with that. That's 1. That's A. I'm going to change colors just so you can see it. I'm going to go to 0. Okay, so 1 is that 45-degree angle. Okay, they don't have to be real long. All right, 0, 1 is up here. That's -1, so that's a 45-degree going this way. Okay, -1, 3, sorry, 0, -1 is over here. That's 3, so that's pretty steep. Now we do have a 4, so you have to make a distinction between them. Okay, so 3, let's say we're going to go up. We just, again, this is crooked, but this is 1, this is steeper. That's all you don't worry about. Don't worry about, oh, is that, blah, blah, blah. Okay. Then we have the 2, so that's somewhere not as steep as this one. So at 1, 0, we're at 2. So that's just make it a little bit steeper than the 1, but not as steep as that. Okay, we have a 0 at 1, 1. I like the zeros. And then 1, -1. We have a 4. So again, we're steeper. We're almost vertical. Okay. And then 0 again at -1, 0, and -1, 1, we're at -2, so we're steep, but we're going this way, negative. And then at -1 is +2. Okay, that probably should be steeper because it doesn't look good. Let's try that again. Remember, this was 3, so not as steep as that, but a little bit steeper then. Okay, so that's what they're going to be looking at, is the relative steepness of your things, if you can just work on that. Okay, so that's the slope field. I don't think we'll have any issues, but that's kind of how they would do it. All right, again, I pasted this just so we remember that we're dealing with this for the whole thing. Okay, so part B says, let's see, find the second derivative. We haven't seen that for a while, but that's the second derivative. Okay, and in terms of x and y. Okay, so well, that's pretty. Describe the region, after you do that, describe the region in the xy plane in which all of the solutions to the differential equations are concave down. Okay, so what does concave down have to do with second derivative? All right, well, concave down is when the second derivative is negative, if you recall. Okay, so I'm just going to write that just to remind myself, and you know, they may just give me credit for the theory too. Sometimes they are looking for that specific stuff. Okay, so let's find it first. So dy dx, oh gosh, what the heck? All right, I'm doing dy, hello, dy dx equals x minus 2y plus 1. I'm going to take the derivative of this and the derivative of this, and that's going to be my second derivative. Okay, so this is just going to be my second derivative, so I'm just going to leave that alone. Remember, we don't manipulate both sides of the second derivative. Okay, so it's derivative of y with respect to x. X is normal, so that's a 1. Okay, then we have to go to the implicits. So 2 dy dx, and the derivative of the constant is 0. Okay, so the second derivative, we know what this is, because remember they said in terms of x and y, so that means we got to replace that, so that equals 1 minus 2 times, remember what the first derivative was, it was up here, x minus 2y plus 1. So let's just take care of this algebra here. What is that? 1 minus 2x plus 4y minus 2. The second derivative, let's put those two together. That's negative 1 minus 2x plus 4y. That's my second derivative. Okay? I'm not going to rewrite that. All right, so that's my second derivative, and then it also says in part B, describe the region in the xy plane in which all the solutions are concave down. So now we need to know where this is less than 0. Okay, so if you describe the region, you don't need to like find it. We're not going to find x, you know. Remember what this would be. This really would be an equation. So let's put it y mx plus b form. So 4y, let's throw our negative 1 over there. So that would be a 1. And 2x would go over there too. Okay, divide by 4. And so y is less than 1/2 x plus 1/4. So remember when we did the inequalities, you know, in Algebra 1, we could graph this, we'd have 1/4, we go up 1/2, da, 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 and then we'd say, is it this half plane or this half plane? Of course, it would be this half plane. So to describe that, you would say, all right, the concave down region would be below the line y equals 1/2 x plus 1/4. That's the second part of the equation, and then that's the third. And, you know, I haven't been an AP reader, but I know I would appreciate you identifying the answers for me. Okay, so that one's kind of a weird, like, okay, so we're looking for, we hadn't done this before, the second derivative in terms of the differential equation, so that was new, but then the concavity was something, remember, that we had to remember from back when we were doing derivatives. Okay, so let's try one more piece. Again, I just reminded us that that was here again. That will be at the top of your page for all of them. You just got to remember that it applies for everything. Okay, so C says let y equals f of x be a particular solution to the differential equation with the condition f of 3 equals 2. Does f have a relative max, relative min, or neither at x equals 3? Okay, I remember, I wanted to remind you that of the, let's rewrite this, second derivative, if I can write it without, maybe I'll just copy it because it's a mess. Oh, there's a little sneak peek of, okay, rectangular, let's do, here it is. Oh, what happens? All right, here's my second derivative. Come on. Paste. Okay, here's my second derivative. I just wanted to bring it up here to remind that we have that. All right. So, and again, this would be all on one page if it's regular. So let me go back to single page. Okay, so this is your second derivative. And remember we had a first derivative test where we had to do the interval testing. Okay, that would require critical value. They're basically telling us this is the critical value. Okay, so we don't know the f of x, number one, and that would be require solving it, doing this, you know, and we really haven't done that much, so I'm trying to get away with not doing that. So we don't have the y equals f of x, we have the derivative of it, and then we also have a solution, and if you notice that solution here matches this number right here. Okay, so what we want to do, they're telling us that let's work with this critical value, and let's, instead of doing interval testing, let's do the second derivative test. Remember how that works? The second derivative maximum and minimum test. If you don't, you might want to revisit that one because you're going to use it on your own too. Second derivative test is a test for relative, max, or min. Okay, and we did it in chapter 4 when we were doing all that concavity, all that business. Okay, and many of us chose not to use it, but I think it's a good one to use here when we're dealing with the DFEQ, because now we have the second derivative. Okay, remember the second derivative test. This is how it works. It says if we end up with the f second derivative, I'm going to use the old notation just because it's quicker, at a critical value is positive, remember, because this makes it concave down, that would be second derivative would be a concavity. If it's positive, it's concave up, that would make it a minimum. Remember that? If f double prime of a critical value is negative, it's a relative max. Because of the whole concavity, if it's negative, it's concave down, so then it looks like this with the max. Okay, so that's the theory that we need to recall. All right, so let's see at 3, 2. So dy, dy, d, I forget how we write this. Okay, yeah, that's what I was thinking. This goes, let me try that again. Okay, d squared y, that's just x squared equals -1 minus 2x plus 4y. Okay, this is a second derivative test, so we want to know what's going on at 3, 2. That's where we're getting this from here. Okay, so we're doing this kind of notation where we just put in 3 for x. All we want to know is positive or negative. So -1 minus 2 times x plus 4 times y. That's -1 minus 6 plus 8, which is going to be, what is that? -5 positive. Okay, so that means that at x equals 3, f of x is, has a relative min because the second derivative is, not my writing is can, second derivative is positive. That's our explanation. Okay? And that's in that problem. Okay, so really, that's what I'm going to talk about. Oh, look, I knew you'd miss my little face. Okay, so the next thing you want to do is you're going to get out, let's see, we call it step by step, and the two documents are together. They're 70 and 71. I've got crossed out what I don't want you to do. 71 is totally good. And there's a piece on 70. This is totally fine. There's a piece on 70 that I got crossed out, so that means I don't want you to do it. Okay? So I want you to give those a good shot. I also want to give you the answers. So hold on. I want to give you the answers to the even exercise here in a minute. Let me stop. Okay, so the answers are 2, 10, and 12 are going to be on here. Okay, I didn't really think you wanted to have me watch me write these, but here are the answers to 2, here's the answer to 10, and here's the answer to 12. So I hope you don't have any trouble, but if you do, let me know. I'll be at my office hours, I guess. Let's say 3 to 4:30. Good luck. See ya.